we're going to do electrodynamics. Well, not just electrodynamics, relativistic electrodynamics. And as you guys all know, this is about relativity and electrodynamics. And when I came in earlier, I actually saw some of the stuff that I was going to say today, but maybe in a less relativistic fashion. I understand that this is also where electromagnetism was given this morning. So, okay, good, great.
That was all Dion's work, by the way.
Oh, was it all yours? Yeah.
Well, it was our group effort.
Okay, but I saw that you've proven that the curl of the electric field is 0, right? All right, good. So, today we're going to creep towards relativity. I'm certainly not here to discuss the exact same thing that Benedict is also has told you last year or is telling you this year. Because our focus is going to be different. Now, of course, last week we started by re-familiarizing ourselves with electromagnetic fields, so of course the Maxwell's equation, but this week is where we're going to start to make things slightly more relativistic, and the next lecture we're going to make things fully relativistic, and then we're going to work from there. Now, in order to do that, before we're going to dive into the quantitative stuff, I would like to tell you where you can already see that relativity has to be in there. Yes? And there's 2 examples that I would like to give. Number 1 is the following. It's this thought experiment. We're not going to do any calculations, but suppose that Raquel here is charged. Yes? So you can decide to be plus or minus. Let's go with the plus. Okay, good. She's a plus charge. I'm sitting over here, and I also happen to be charged. Right? So I can measure right here, right now, by the amount of attraction that I feel or the repulsion, whether how strong the electric field is due to her, and some number will come out. Agreed? I mean, you know the formulas, blah blah blah. How much magnetic field is there for me?
You're stationary, not moving.
Yeah, well, both of us are not moving. So for magnetic field, right? If you take the 4th Maxwell's equation or the 2nd Maxwell equation, for magnetic field, what you need is either a current or a moving charge. And we discussed last week that those 2 things are not strictly the same thing in the circumstances. But she is not moving, so she might be charged, but she is not moving. So that means she is not producing a magnetic field. Secondly, the only way that I, as a charge, can feel a magnetic field is if I myself would be moving. Yes? Charges do not feel magnetic fields, moving charges feel magnetic fields. You remember the equation for the Lorentz force? It specifically contains the V of how fast you yourself are moving. So just the fact that you have charge does not mean you measure magnetic fields. So if she is charged and I am charged, I'm sitting over here, I'm just feeling an electric field and no magnetic field. Even if she started moving, so she makes a magnetic field, I would still not feel it because I myself had to be moving. Okay? So that means I really, really, really feel no magnetic field sitting over here. Now, if we would change the situation, that is by I start now moving with respect to her, then all of a sudden, her charge in my inertial frame, let's assume that I go from one inertial frame to the next inertial frame, and you guys all know what an inertial frame is. That means that all of a sudden, she is now a moving charge. In other words, she is now a current in my new frame. So if I measure an electric field, do I get an electric field now? So I'm in this frame now, moving with respect to her. Do I measure an electric field? She's all careful nodding. Yes, she still has charge, I still have charge, so that we still feel the magnetic for the electric field. But now, in my frame, she is a moving charge, or in other words, she is a current. So in my frame, all of a sudden, she makes a magnetic field. But since I myself am also moving, that means I also am susceptible to that magnetic field. So all of a sudden, the amount of electric field and the amount of magnetic field seems to be highly dependent on inertial frames. In one inertial frame, one of them was 0, the other inertial frame, the other one was not 0 anymore. So from this very easy example, you can clearly see apparently you can turn magnetic fields and electric fields into each other. You know how this works, yes? Maxwell's equation tells you if you shake an electric field, you get a magnetic field. If you shake a magnetic field, you get an electric field. But apparently you can also do it in a different way, namely just by going to another inertial frame. So there is some connection between magnetic fields and electric fields depending on inertial frames. Now, that's quite interesting. That already tells you that going from one inertial frame to another, and electric and magnetic fields are in some way connected. Yes? Note that I haven't used relativity yet per se. I just said moving. I haven't said with the speed of light or something like that. Now, here's the second example that I promised. In the exercises of last week, we're not going to recalculate it. I'm just going to point you towards the main conclusions. 5.13, I think, yes. I pointed you towards it in my email of last weekend. I gave you a full written solution, so I hope you've looked at it. If not, that's fine. Make sure that you studied it at some point. I will just tell you the gist of it. If you have two wires, and both of them are charged by a certain charge density, so the amount of current, amount of charge per unit length, centimeter or so, then if I am now standing still next to these wires, then I will conclude that the only thing that they feel is an electric field, right? It's a wire, but the charge in that wire are not moving, so there's no current, it's just charge. And because this has the same charge as that with some number that is unspecified, you know that there must be some electric field, and you also know that they should be repelling each other. Agreed? Okay, now the exact same situation, so the wires stay as is, but now the only thing I'm changing is I'm going to go to a different inertial frame. So that's what I'm doing right now. And I'm still looking at the exact same situation. And just like in my example with Raquel just a second ago, that means, wait a minute, to me both of them are now not just charges, both of them have become currents. So this guy has a current, this guy has as well, but this guy has a current, so this guy makes a magnetic field. And because this guy in my moving inertial frame has a current, that means he is susceptible to that guy's magnetic field. So that means all of a sudden there's not just an electric field, there's a magnetic field. And the magnetic field will give this extra amount of force between the two wires. Now, if you go through that will be the Lorentz force. This Q, V, cross B. Now, if you go through the exercise, then you can easily convince yourself that this particular force is actually pushing the wires closer together. Yes. Yeah, you just use your the right-hand rule if you want.
Yeah.
Okay. Now, I hope everybody at some point will drop the left and right-hand rules from high school physics. Yes. The real reason is, of course, that this guy is given by this guy. This is your right-hand rule, okay? But sure, if you want to use, or you're free to do that. But yes, if you use the right-hand rule, you can tell that the magnetic field is pointing in or out of the board. Then the Lorentz force itself comes with the inner product, so that means that the force that it feels is perpendicular to the magnetic field and to the current. So that means it has to be along this direction, and you can easily convince yourself that magnetic fields will pull each other inward, right? Now here's the beautiful thing. Here's by the way where you see the same example as with Raquel just a second ago, that you can turn electric fields slightly into magnetic fields by just going to another guy's inertial system. But here's the beautiful thing, and here's where relativity starts to show its head. The beautiful thing that happens now is that if you go through the exercise, you will find that the Lorentz force trying to push the wires together will never be bigger than the electric fields trying to push them apart. If you go through the exercise, you will find that, well, it's dependent on how fast you are moving. And you will find that the only way that this guy exactly counteracts this guy is when you go with the speed of light. Now, let's switch off that we already know something about relativity right now, yes? That you know, oh, but wait a minute, you cannot go with the speed of light. So therefore, there's no inertial frame where the magnetic force is bigger than the electric force. By the way, let's switch on relativity just for a second. Why? And then we'll switch it back off again, okay? Why can I not go with the speed of light in that direction to make this Lorentz force using the V bigger than the electric field? What is stopping me from just going with 2 times the speed of light or so? You've all done relativity? Sure you have the answer somewhere?
Well, you would need an infinite amount of energy.
Yes, agreed. We derived in period 2 that in order for any mass, and I'm a mass, unfortunately, when I move this direction, that you need an infinite amount of energy once you hit the speed of light. Now, please, 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 and I'm very happy nobody did that, please don't say because the mass has increased, okay? that's simply wrong, and it should be banned and put to death with fire. Okay, that concept. No, it really is because of the energy that you need. So in other words, even if I try, I cannot move fast enough to make this V big enough, to make this force big enough, that this guy becomes bigger than that guy. And here's the good news. Because that means that no matter how fast I am moving, in whatever inertial frame I go to, the two wires will always push each other away, because this guy will always win from the other one, right? Now, why is this good news? It's good news because if that was not the case, so let's switch off relativity. Suppose that we didn't know that you could not go faster than the speed of light. We would have a very strange situation. Because if I would look at the wires while standing still, no Lorentz force, I will conclude they're pushing each other away. Yet if I start moving, and if I move fast enough, then all of a sudden I could see them pull themselves together again. Now that is a paradox. And not the kind of relativity where if you put in some loss of simultaneity and all of a sudden the paradox is gone. No, it means wires either move either towards each other or away from each other. You cannot remedy this in any way by invoking some principle of relativity or something like that. So we can already see that there's relativity here. Apparently, in order to stop this from happening, that if you go to some other guy's inertial frame, all of a sudden the actual physics changes, the wires don't push each other away but start pulling each other towards each other, the only way to stop that from happening is apparently by assuming that one cannot go faster than the speed of light. That there is something about the speed of light that is special. You see the argument? This is why I ask you to switch off relativity. Let's assume you didn't know that the speed of light was special. If you want not to end up in a situation where, depending on how fast you are moving, wires either pull each other, get close to each other or push each other away, that would be extremely unphysical. That the amount of force that they feel or the distance that they push each other will be dependent on how fast you are moving. In order for that not to happen, apparently, something happens at the speed of light that prevents this from happening.
But why would that be so strange?
It
Why would that be a paradox?
Because you have two different outcomes in the same
Yes.
setting. You would see
Yes,
it
but
means
like in
that
quantum
different
mechanics, you have that like all the time.
Yes, but no. Let's put in my favorite example again, okay? I've hooked this up to some machine, and let's be completely unbenign. Let's say that the unspecified third party I was talking about earlier is actually bad for safety. They built a machine such that if the wires touch, then this atomic bomb will go off and the Earth will explode. Okay? Then that means if I stand next to this thing and I don't move with respect to the wires, I will say, look, the wires will never touch because the electric field will always push them away from each other. Earth will not explode. But yet, if I start moving and I do it fast enough so that the magnetic field or the magnetic force becomes big enough, and this guy wins, then in my new frame, all of a sudden the Earth will explode. Now, surely I hope you agree with me that the Earth exploding or not exploding should not be dependent on how fast I happen to be moving along the wires.
What if you set your experiment such that if it only moves to a certain distance down, that the Earth explodes, and then if you move fast enough, you would prevent the world from exploding, and if you move slow enough, the wires would be more.
Yeah, but by what physics? Because you're now inserting that then apparently at some higher velocity still there's some new physics coming in or something like that.
Well, I'm saying that if there is no, like, if you're not moving, if it's just like the wires are still go closer to each other.
Yes.
But then if you're moving, they get less close to each other because you introduce magnetic field, which is such.
Sure.
Yeah, and then you can say, okay, let's say just if the wire gets closer to each other by an extreme amount, then the world explodes. But if it just like goes together for a small amount, it does not explode. So if you would be stationary, the world would still explode, while if you moved fast enough, it wouldn't. You just change the line where the world would explode, what curvature of the wires.
Well, like you're saying in a Minkowski diagram or something like that? Or just thinking like how you're just setting parameters?
No, I mean what you're saying is, well, they don't have to touch, they just have to cross a boundary here or something like that. But how does it change my example? How does it change my paradox?
It doesn't change because the electric force is always bigger than the magnetic force.
Yes.
So there is no way that magnetic force will be big enough to even go close to that.
Yes.
Yeah, but
No, I think
because like
kind
because if you don't have the magnetic
draw.
force,
Please.
then it's going to be closer. And if you have it, then it will be so like the magnetic force counteracts the electric force. Right? So
Then
if you don't
So
have
I
a
guess
magnetic
you
force,
have
it will be
the
closer.
case where they would be like
They
this
just happen
close
at
to each
different
other,
times,
and then you would also get
They
the
would
case
still
where
move
they
away,
would
but
be
just
this
slower.
close to each
Right,
other,
in the other
depending
frame,
on the velocity.
time would go slower, so it would
Right?
happen.
Mm-hmm.
The same event
This
would
is
still
bigger
happen
than
eventually.
this.
I'm not seeing it because
But this is possible physically.
no, I'm trying to see what it is that you're drawing right now.
Oh, so this is
Yes.
the previous location of the wire, like if they were not charged,
Yes.
like if they were just straight. And this is now you have a charged wire, so they get closer.
So this, if you were standing still, this is what you would see, is what you're saying.
Yeah.
Okay.
And then you move and magnetic field comes into play, and then this distance changes. It's not the same.
No, okay. Actually, no. Okay. Oh, I love this actually because it shows as an example that there's two different types of paradox if you think about this. Yes. Remember, in relativity, you had paradoxes that were not really paradoxes. It looked as if they're counteracting each other, but usually you had to take into account the loss of simultaneity or something like that. And if you would take that into account, there was no paradox. And you have actual paradoxes where things are actually different in two inertial frames, and there's no way that you can invoke that. Your paradox is of the first kind, because what you're saying is, oh, but if you start moving, then the magnetic field is pushing them away a little bit, so that means the dent towards each other is slightly different. I agree with that, but as I keep on moving, the electric field would win, would keep on winning, so this, a couple of seconds later, would have become this. It will be a couple of seconds later, but at some point I will end up with this situation. It would just need not be at the same time, at the same moment in time. Yes, being if in your situation where there's now also a magnetic field trying to counteract the pushing together, yes, that's fine. That means it takes a little bit longer for the wires to get it to this position, but they will get there. It's just at a later moment. That's a loss of simultaneity issue. So the Earth would still explode in both cases, it's just a couple of seconds later.
Because actually you can never compensate totally the electric force. So
Agreed.
the magnetic force will just more slowly bring out.
Exactly. So that means that the explosion would still happen, it's just a couple of seconds later. That's a loss of simultaneity paradox. That you can resolve by saying, oh, but wait a minute, if we compensate for the fact that there is a loss of simultaneity, then you can compensate for it.
Well, what if we set our explosion button here, so at one moment the wire comes here, it explodes, even if it goes later, like back. Like in this case, you would never get to this explosion button, while here you will get to this explosion button.
But because
Wait, why it
resulting
still had
force
to-
is not zero.
What?
So that's the difference. Like the resulting force is not zero. So if you moved at the speed of light, the resulting force would be zero, and the two forces compensate each other. So
Yeah.
then nothing would move. In that case, the wire is going to continuously move towards tending to be what is at the end. Like what is the
So it has to pass through that point
That's what
anyways.
you're putting in.
And this is irrespective of where you've actually put the point of explosion.
It's
I'm
still
confused.
about
Okay.
but it's just
different setting.
Do people see that there's really two types of paradox here? The one that Elisa brings up is you can compensate. Yes, we can actually make an exercise out of this and just get the numbers out at some point. But just get the physics out right now, yes? If you go to another guy's inertial frame and there's a magnetic field pushing these wires a little bit out, so they don't move as quickly towards each other as they would have if you would have stood still, then yet in this frame, yes, the magnetic field is compensating a little of the electric attraction, but not all of it. So that means it will still accelerate towards each other just by a different amount. So that means it takes a couple of seconds later for them to cross any point where the Earth will explode. So it just means that the effect will still happen just later. Well, that really is a relativity issue. Now, there's no way that you can, the other paradox that I brought up is one that you can simply not compensate. It's either explosion or non-explosion, yes? So even if you had no idea about relativity and about loss of simultaneity, you would be very puzzled by this one actually, if you didn't know the loss of simultaneity thing. But if you go to my original paradox, then there's absolutely a clear indication here that something must happen at the speed of light. There must be something about the speed of light Because if you cross that number, if you start moving faster than the speed of light with respect to that situation, then you would have this real paradoxing go on. So that gives you a clear hint that electromagnetism, this situation, has something with the speed of light built into it, even though it's not clear. It's the only thing I used were the Maxwell's equations, but apparently this comes out. There is something about the speed of light. So these are my two examples, right? You can really tell something must happen there. There must be something going on with the speed of light and or with, in retrospect, relativity. Now, this is where we're going to go to. I want to show you explicitly how that works. It's going to take us 2 lectures to get there. The first thing that we have to do, and that's our main goal for today, is if you want to make things relativistic, you need 4 numbers. Because space and time come in 4 numbers, and as you know, relativity is a space-time theory. 1 time dimension, 3 space dimensions. So that means if you want to make anything relativistic, you have to in some way bring it back to a space-time phenomenon, and those come in only 4 flavors. 3 directions in space, 1 in time. Now let's write down the Maxwell's equations. Equations are these? It's a trick question.
4.5.
4.5? Why the 0.5? I thought numbers of equations came in discrete numbers, but how many?
Can we say 2 because they come from 2 equations?
But you also need continuity equation to get the
Okay, so 3.
Yeah.
Okay, 3. We did prove
1.
last week that you get all these from only from 2 experimental facts. I agree with that. Yes. So let me go there in a second. Now, suppose that somebody gave you this instead of the Biot-Savart law and the Coulomb law that we started out with last week. How many are these? I mean, they look like 4, but they're not.
Oh, can we like do a reverse process to get to what E equals and B equals? Like doing some kind of integration? Like if you were given, like if you give this to a mathematician and
yes,
he like does some kind of integration, like or uses like one of the 3 theorems or something.
yes.
Kind of arrives at what E and B is equal to.
No, you're right. You would get. I mean, I see where you're going. What you want to do is get these equations into their. What we now have is some derivative of E and B gives you something else, right? I mean, all these are really just derivatives, spatial derivatives. But you're saying, well, let's first write these into this form: B equals something something and E equals something something, right? To get rid of the derivatives. You can do this. You get some new equations that are equivalent to these, and those are called the Maxwell's equations in integral form. I actually have a T-shirt with these Maxwell's equations on them in integral form because it looks more complicated, and you can make yourself look cool by having a cool, complicated shirt. It actually says, and God said, brrr, and there was light. And it was the coolest shirt ever. Unfortunately, I bought it when I was 19. No, 20 on a student trip. And there's a little bit more of me than there was back then, so it doesn't fit anymore, but I still have it. But no, you could do that. It would not actually change the answer to my question. So let's suppose that we have done this, right? In fact, this was actually our starting point of last week, because this will give you the Biot-Savart law, this will give you the Coulomb law. Well, let's do the counting here. How many equations are this? 2. It's a true question.
I mean, unless you assume relativity, because I remember you saying something like B is the Lorentz contracting
Yes.
field, but like you wouldn't know that.
We've switched out relativity for now. Let's be historical and suppose that we never had seen that before.
Well, maybe if you know that electric fields can cause magnetic fields.
Yeah, we don't. Because you need relativity to do that.
Okay.
It's really a trick question, guys. I mean, yes, there's 2 equality signs, but this is a vector, so it comes in 3 directions. And this is a vector comes in 3 directions. So that means this is really just shorthand for 3 equations. And this is 3 equations. So you have 6 equations here. In fact, you also have 6 equations in their original form, because this is a scalar equation, so that gives you 1. Right? I mean, despite the vectorness here, the inner product is a scalar, so this is 1 equation, that's 1 equation. This vector equation has 3 directions. This vector equation has 3 directions. So quickly adds up, yes. You get 8. So, if we want to make something relativistic out of this, we will actually need 4. There's some superfluous information in there. And in fact, we already knew this. If we go back one more time to the situation with Raquel, suppose that I would have wanted to know the amount of attraction or repulsion between me, a charged particle, and her charged particle. If I would have done this from this system, as we were concluding, that means I have to first calculate the electric field, that's 3 numbers. And I also would have to calculate the magnetic field, because we're moving with respect to each other, so she makes a magnetic field that I feel, so that's another 3 numbers, 6 numbers. Yet, if I would have just stayed here and not moved, I would have only had to calculate 3 numbers, right? Because the magnetic field I don't need anymore. So I really don't need all 6 numbers. So you can tell that there is some relationship, and Michaelis, this was what you were saying, I think, that there is some Lorentz contracted version. You only need one of them, and then you need the other. So this is sort of hand-wavingly talking you towards the fact that you don't really need the B field. If I just choose my inertia frame correctly, namely one in which there is no B field, and just electric field, I just can calculate this one, and I have all the information that I need. The wire example is actually a good example of that. Because there were two inertial systems. If I would have moved with respect to it, I would have had to calculate the electric field and the magnetic field, as I do in my worked solution that I posted on Aleum. Then I needed to have calculated 6 numbers. Yet if I would have stayed stationary with respect to the wires, I would have gone to the inertial frame where there's no moving going on. I only needed to calculate the electric field and I was done. Right? So, yes, if somebody gives you an inertial system, chances are that you have to calculate both these numbers. But if you know that you should be able to choose any inertial system, that means you can just choose the inertial system where there's no B field and you only have to calculate 3 of them, right? So you can really tell that these equations, there are just too many of them. Okay, so if that is now going to be our conclusion for now, that you only, if you choose your inertial system correctly, you just need the electric field. 3 numbers. There's still some other thing that you need. It was mentioned. You still need the continuity equation. Yeah. Because if you go to some other inertial frame, that means that something that used to be stationary is now turned into a current. And that's what this equation tells you. So really, if you think about this, these are really the only couple of equations that you need. Just go to the inertial system where the magnetic field is 0. Calculate using Gauss's law or so what the electric field is. If you then want to go back to the original inertial system where there was a magnetic field, fine. You use the continuity equation in some clever way, and then you get your full solution. So, what is the point here? You really need just 4 equations. Now, for people who want to build in relativity, that's good news. Because relativity requires you to have 4 numbers that are related to each other. And you can tell, despite this complicated looking set of equations, that yes, ultimately it's really only 4 numbers. All clear on that point? Because now the question is, okay, but what are these 4 numbers? Yes, I mean, you have 8 equations here, but they're highly superfluous because you should only need 4. We can actually see from these considerations that you would only need 4 ultimately. So let's find a way that we can turn them into 4 equations that have all these exact same information as these Maxwell's equations. And once we have done those 4 numbers, then we can see whether we can make them work within relativity. But the first requirement is that we have 4 of them and not 8. So that's my plan for today. Let's find those 4 numbers. Yeah? Now let's make things quantitative. Is everybody clear on this style of reasoning?
Mm-hmm.
Good, good, good. Now, part of this you probably have already seen in your electromagnetism course, because I'm talking about potentials. Now, when Ben explains this to you, I'm sure he explains it in a mathematical context, that this is possible to do this mathematically. namely that these four equations can be summarized by only two, well, it's actually four, scalar potential, what we call the vector potential, and these are your four numbers.
I think he only explained scalar potentials.
He did? He didn't do this one?
Not
I'm
yet.
sure that he will. But that's why we're here. So in the electromagnetism course, you will also learn about these, but there it's just a mathematical novelty. Oh, you can also do it like this. For us, it really has a physical purpose. Four numbers means you have a starting point for relativity. It's not all of it, yes, you need four numbers and some additional stuff, but it starts with having four numbers. So let's redo this calculation, how we're going to get these four thingies into, these 8 thingies, 1, 2, 3, 4, 5, 6, 7, 8, into only 1, 2, 3, 4 numbers. Yeah? Now, let's start with the magnetic field. Let's start with Maxwell's second equation, actually. As you know, Maxwell's second equation tells you that the magnetic field should be always such that its divergence equals 0. Good. Now, there is a mathematical theorem that we're going to prove in the tutorial that says that if you have the curl of any vector function f, and once you've taken the curl and then you take the guy's divergence, that this is always 0, regardless of what f was.
Oh, wait, did we do that already?
Yeah.
Did we do this already?
Yes.
In the previous tutorial, I think.
Where did we use it? Oh, you're right. Yeah, of course. Yeah, no, that's right. No, good. So we've already proven this. Good. That means we can immediately apply it here. Because look, that means that if you would just call this particular combination B, you get back Maxwell's second equation, right? So apparently, mathematically, you're perfectly allowed to say, well, this B thingy here, might as well write it as the curl of some other thingy. Completely free to do that. Because mathematics says, well, you get 0 either way. So from this mathematical fact, we're going to introduce a new thing. This A. This A is what I called F here. And I hope everybody now sees this second Maxwell equation, and this mathematical fact tells you that you should always be able to write B in terms of the curl of some new function that we call A. Now this A is what we call the vector potential. Good. Now this by itself will not bring you anything new. It's just a mathematical rewrite of something you already knew, namely Maxwell's second equation. The question is, okay, but what does A then obey? Yes, it obeys ultimately this one, yes, but this is what you put in. You get the existence of A from this guy and that guy, so it just means that A exists. But now the question is, what does it obey? If I were to give you a certain amount of charge and current, and I ask you, please calculate A, how would you do it? Not using this. So we need some equation that tells you, and A is blah blah blah. We have what A does. Once you have A, how you get back your magnetic field, but we haven't said what A is. So we have to get it from somewhere. It's not from here, because this one we have already used. Now take a guess.
I guess the other one with magnetic fields?
Yes, agreed. You can get it from here, yeah, or from here even. But let's make things simple for now. Let's assume that we're first going to do this exercise in case there's no time-changing electric or magnetic fields. Now, you understand this is not the most general situation, but it is didactically easier to get there, and then I will show you how you can remedy for the fact that there are actually changing magnetic and electric fields. So for now, let's assume that this guy is 0 and that guy is 0. That means that if we want to know what A does, we cannot use this one anymore because now in our particular situation this one does not contain a b anymore, so we really have to use this one, right? Alright, well, let's do it. The fourth Maxwell's equation tells you that the curl of b is equal to the current. So the curl of b should be equal to mu 0 times j, but b itself, we have now concluded from the second Maxwell equation, is itself a curl. So you get the curl of a curl, and all of that should be equal to the current. I'm just using the Maxwell's fourth equation now. So this one is now also used. And there it is. If I give you a charge, and you're clever enough, not a charge, a current, is if I now give you a j for a given situation, and you're clever enough mathematically, you can work out what then the resulting a is. Right? Now, this is not a very handy way of using it, so I'm going to rewrite this in a slightly more comprehensive way. Namely as follows. We did not do this one, did we? Last time. Okay, then let's solve this one during the tutorial. That the curl of a curl can be written as this thing that we call the Laplacian. And then there's a minus the gradient of the divergence. That this is true is mathematics. There's no physics in it at all. What we then have is the following. An equation that tells you what A is if you know what J was. As you can see, I flipped the minus sign. That's the conventional way of writing it. But that's it. Now, let's take a step back and just parse this physically. We started out with saying we have these two equations. Yes, 1, 2, 3, plus 1, that's 4 equations. And using the fact that this is true, and then using Maxwell's second equation, we found out, well, the magnetic field is just as easily calculated by first calculating A, taking its curl, then you get B, and the A itself comes from here. That's only 3 equations. 1, 2, 3. This is a vector equation. That's good. We've removed one of these superfluous equations in the Maxwell's equations, because the ultimate one that we now have to solve is only 3 equations. And we started out by having to solve 4 for the magnetic field. We've removed some of the superfluousness. Good. We started out with 8 numbers, we had to go to 4, we've lost 1. That's good news. Stop the madness. It will get better. Because this equation, yes, in principle is easy to solve. Well, it's not easy to solve, but you can solve it. Somebody gives you a J, you do the math, you find your A, and then you have your B. But wouldn't it be nice if we can not only make this equation look simpler, but secondly, that the equation that then remains, I just give you the general solution for any situation. You don't have to do any solving anymore. Wouldn't that be a nice way to go into a break in a moment? So let's do it. After the break, I will show you that you can actually make this guy disappear. The sarcasm is telling you it's beautiful, it really is. Okay. I will tell you in a moment why that is. You can make this guy disappear. I can quickly give you the argument, and after the break we will show you quantitatively how it's done. But if you recall, your B field is given by the curl of this new A field, yes? This vector potential. After the break I will show you that A is not unique. There's multiple ways to, you have multiple A's that all of them give you the same B. So that means if you're interested in the B field, you have a certain amount of freedom which of all the possible A's give you the same B, which one you choose. And I will show you after break that of this plethora of A's that you could have chosen, there is one that makes this guy 0. And you get back the exact same magnetic field. Now, if you have that freedom, it's called a gauge freedom, you make use of it. Because once you have done that, you will end up with this equation. Which is much easier. So, just give you the argument one more time. There's more than one A that gives you the same B. And because you have more than one A, you have a choice which of the A's to use. That will give you the same magnetic field, so it doesn't matter which one you use. And I will show you that there is one A you can choose such that that particular A has its divergence 0, and therefore this term drops out. You end up with a much easier equation. And now it's the general solution. Because this equation has a well-known solution. It's called the Poisson Equation, for the people who care to look it up. The Poisson Equation was solved long ago, I'm assuming by Poisson. I will give you the answer. If you want to know what the vector potential is at a particular position in space, R, and I've given you what the current is at any point in space, the only thing you have to do is take your J, the one that's given to you, the one that defines your situation, give its argument R prime, what I called the sweeping R last time, divide it by capital R, and if you recall, that's the difference between the sweeping R and where you are looking. Now last week we also had an equation like this, but back then it was R squared. Now it's just an R, and then you integrate over all volume. You know this? Here's the good news. We started out with, if we had these equations, again, first of all, we had 4 equations that define the B field. 1, 2, 3, 4. That's too many equations if you want to do relativity. But by mathematical freedom, you can reduce it all the way here, and that's only 3 equations, so we've lost some superfluousness. That's one. Secondly, this equation has a general solution. So if somebody comes along and says, hey, I want to know a magnetic field for this very complicated current, you say, okay, I'll take your current, put it in here, do the integral, get my A, take its curl, and there's your magnetic field. Much easier than doing it in this way. Jort, you had a question, I think, a second ago.
Yes, the R had just disappeared, or is there a specific reason?
Oh, yes. No, that's a good point. That is a good point. Thank you. Yeah, in the last week we had something that had an R hat in there because it showed you in which direction the thing was pointing.
Right, but didn't you say that this is a vector?
Yes,
potential?
so this is already vector.
So it is in what?
It's in the same direction as the current.
Okay.
If the current is moving in that direction, then
so
the A field
J
is also
vector
pointing in that
current.
direction.
Okay.
That, by the way, is different than a magnetic field. The magnetic field says if the current is in this direction, then, well, here's your right-hand rule, then the magnetic field points in a different direction altogether. So, this has some aesthetics to it. You don't have to worry about directions. It's just in the same direction as your current.
And volume is based on what coordinates?
But that doesn't quite matter. So let me draw you a picture of what it looks like. There you go. Here's your space. You are standing over here from some coordinate system. In fact, let's make it visual. This is the origin of the coordinate system. You are now a current. So you're moving in any direction. You don't have to move, but suppose that you are. You're moving that direction over there. Yes. And I want to know how big the magnetic field is due to you at, well, I need to volunteer. Well, I'm going to take Giovanni just because. So here's the origin of the coordinate system. There's the current. There's Giovanni. And I want to know how strong the magnetic field is at his location due to your current.
How strong his magnetic field is.
How strong he feels your magnetic field.
Oh, how strong he feels my magnetic field
Yes.
at his location.
So the only thing you have to do, I have to take, this is the origin, I have to take the distance where he is, that's what I call this r.
So he's r hat.
No, he's just r, this r.
Oh, sorry, r vector.
R vector.
Yeah. I'm r prime.
You are r prime.
Okay, I get this now, yes.
And then we integrate, and this big R, that is your
distance. Okay.
And it makes sense, right? I mean, if I want to know how strongly he's affected by you, I need to I need to know your, well, I'm happy I didn't use the word attraction here, okay? or repulsion. But then you need this distance, right? That's this distance. Now, in case there's more than one current moving about, and some of you, other you guys are also currents, that means I have to sweep over all of them. So I have to go all over the volume and look for all the places where there is a current, going over all the r primes. So Pepijn is another current there over there. So that means when sweeping at some point, he will have a current. They will have a mutual distance, so they will have a capital R, and I have to add that to the mix as well. But long story short, we've removed one of the superfluous equations. And not only that, here's a general solution. You don't have to do any, well, you still have to do the integral, sure, but it's much easier than having to pick together the right combination of Maxwell's equations. Gives you everything that you need. Any questions? Yes?
The equation that we got there, it still has 3 equations.
Agreed, yes. But we started with 4. Over here, the magnetic field was scattered over 2 equations, or actually 1, 2, 3. This is vector plus another one, 4. So that's 4. So not only is that unhandy, because it's scattered over 2 of them. Secondly, there's 1 too many in some particular way. This one doesn't have that problem.
Okay.
You should only need 3. And there you go. Not only are here the 3, it's exactly the right expression. So you give me a current, I do the integral, I tell you the A field, and taking its curl, I get the B field.
Wait, but this is when it's only not moving?
This is when there's no changing electric field. If somebody
Oh,
here
just
happens to
no
be a charge
change.
and jumping up and down, this will not work, but I will tell you how that works later today.
Okay.
Yes. Okay, let's have a break. Waffle is worth about 0.01 point or something like that, right?
Everything helps.
Really, if the 0.01 point is making the difference, then you're not doing enough studying.
That would be like,
Okay.
yeah, do you want a box of waffles?
That'll add up quick.
Anyway, so here's a summary of what we did before the break. Just to remind you again, we had these 2 Maxwell's equations. We could already conclude there are too many of them. You should only need 4 ultimately, or 4 numbers. We only want 4 numbers, right? So I mean, I'm really making 2 statements. You should only need 4 numbers, as my Raquel example hopefully showed to you, right? I mean, I could have just calculated the electric field by choosing the appropriate inertial system. That should give me the same answer as that I would have gotten if I had been in another inertial system. So from that I know I should only need 4 numbers. And if I want to do relativity, I need only 4 numbers. Yes? So it looks as if these things are going to be coming together at some point. And here's the first step that we made, because here you have a couple of equations. We showed using just pure mathematics alone that the second Maxwell's equation tells you that there should be something like an A field, the vector potential. The vector potential then, according to the 4th Maxwell's equation, should be given by this equation here. Using something I have not shown you, but I will in a moment, you can make this guy disappear. And as a result, your vector potential only has to obey this equation. And lo and behold, this one has a well-known solution in mathematics. Here's a general solution. So in other words, this guy, this ultimate expression here, solves all of magnetostatics, because I've assumed that there's no changing electric or magnetic fields. So if you have an electromagnetostatical situation, you just have to remember this equation and this one, and you can calculate magnetic fields for any situation from now on out. That's good?
So a quick
Yes.
question, what happened, or why is it not included, the permittivity?
The epsilon 0.
Yeah.
Because the epsilon 0 is a statement on how good the vacuum is to accept the propagation of electric fields.
Okay.
And this is only a magnetic field.
magnetic. Okay,
Yes.
okay, cool.
I don't remember exactly the part where we saw that the divergence of that vector field was 0?
We haven't done it yet,
Okay.
but I will do it now. So let's start with that point. Because you're right, I mean, I claimed that this can be chosen as 0. I haven't shown it to you yet. So let me go verbally through the argument first. The verbal argument is, again, that the A field is not unique, the vector potential. You can turn the vector potential into a new vector potential. We're going to call it A vector prime. Now, for the people with relativity on their mind, I do not mean in a different inertial system. I just mean different function plus extra stuff. In fact, let me immediately give you what the extra stuff is. Now, suppose that I have some function, lambda. Lambda, we also use that symbol to say the amount of charge per unit length. I don't mean that one, I just mean any function.
Is it scalar or vector function?
This is a scalar function. So there's a scalar function. Now, a scalar function you would not be able to add to a vector function because scalars and vectors do not add. But a scalar function and its gradient, the gradient of a scalar function is itself a vector. So this guy is scalar, but this guy is vector. So if you want, you can turn your old A field, vector potential, into a new A field. And here's the clever step. My claim is that it doesn't matter how you've chosen lambda. It's a function, it's not just a number. It could be any function of space. No matter how you choose lambda, this new vector potential, A primed, will give you the exact same magnetic field as if you would only use the original A. I will prove that in a moment, but suppose that that is the case. Then you have the situation where apparently A is not unique. If you want to have the magnetic field, you could have used this A, but you could have also used A primed. In fact, there's an infinite many A primes because you have infinitely many choices for your lambda. That's good. If you're interested in the magnetic field, there's an infinite amount of A fields that all give you the exact same magnetic field. Now, before you move on with that statement, let me prove that that is true. So my claim is, if I know that the curl of my original A field is a magnetic field, and we know that that is true because we defined it as such, then the curl of my new A field, the primed field, will give the exact same magnetic field. So it doesn't matter whether you've used A primed or A, it will give you the same magnetic field. Let's prove it. The curl of the new A field, well, the new A field is the old A field plus this extra stuff, right? So you get curl of the original A field plus extra stuff. I forget what the word was.
Distributive?
Thank you, yes. It's another way of saying you can take the curl of each separately and then add them together. So let's do that. So you get this. But this, the curl of the original A field, is what we call the B field. This was B. And here's another mathematical statement that has nothing to do with physics whatsoever. The curl of a gradient is 0, always. So this is always 0. So what do we have? Then apparently, if you would have taken the curl of the new A field, you would have gotten the same B field as if you would have gotten if you had started with the original A field. And this is true for any choice for lambda.
I have one question.
Yes.
Why does taking that specific divergence of that scalar function causes that part of the equation to become 0? When I say that part, I mean d times dA.
This one.
Yeah. Like, why does taking this suddenly make this 0?
Well, we're not there yet. We have half the argument now. What we now have is that there is more than one A field that give you the same B field. In fact, there's infinitely many. For any choice of lambda, you will get the same B field. So you can see that there's a certain amount of freedom. I will get there in a moment. So there's a certain amount of freedom. And in physics, we call this a gauge freedom.
Is there any physical explanation for this? Or
Not
is it
really,
just math?
no. No, well, yes, there is actually. I will get there in a moment. Let me go through the argument first. But there is a physical explanation. Yes. Let's make sure that we have the mathematics all set. So that means we have infinitely many A fields that all give the same B field. And now, so that's half the argument, the fact that the A field is not unique. And then the next question, and that really is your question, okay, but if you can choose your A fields, there's a whole range of A fields, is there one of these A fields that its divergence is 0? If that is the case, right, so maybe there's an A primed defined in the exact right way that its divergence is 0. If that is the case, you will still get the same B field. It's just that all of a sudden this one is gone. Now, to prove that that is the case, I'm going to leave to you as a tutorial exercise. But you will have, by the end of today, you'll have the answer. The answer, by the way, is yes. Of this infinite range of new A fields you could have chosen by choosing appropriate lambdas, there is one lambda that makes sure that the resulting A primed has a vanishing divergence and this one vanishes. So I'm sorry, I've given you half of the argument, the other half is for you to try to see that it works. I will say, well, anyway, no need. I'll leave that to you guys. Okay. So everybody clear on the, what we call the gauge freedom, that you have a particular amount of freedom to choose this guy, your A's, without having changed the B's. Then I will, in a moment, give you the argument why this is, where there's a physical interpretation. But yes.
Yes, so but it only works because you defined A dash as old A plus the gradient of some
Yes.
function. If you would just define it as plus another vector.
Then it would not work.
Yes.
Yes. So it's only because that works. So when I said let's redefine A as old A plus something extra, I chose the something extra in this particular way because this particular way produces what we see here, the curl of a gradient, and I know mathematically that is 0.
Mm-hmm.
So by having chosen this extra part as the gradient, I enforce that my new A will have the same B. So the choice is deliberate.
Mm-hmm.
And that choice doesn't affect things later on?
No, not at all, not in the slightest. This, so let's put some semantics in there, this is what we call a gauge, and you will go into either particle physics or more theoretical physics related courses or careers. Gauges are quite ubiquitous in physics. If I would have to give a hand-waving definition, then I would say something like this. A gauge is a choice in your mathematics such, or a choice that you have in your mathematics without changing the actual physical outcome. That's what I would call a gauge.
Like phase.
Phase is a good example, yes. Suppose that you're interested in the intensity of light, for instance, yes? Then what you have to do is that you have to take the electromagnetic field and take its modulo square and then integrate it over the volume in which you're looking, yes? But it doesn't matter if the phase of that electromagnetic field is plus pi or minus pi, the integral will give you the same answer. So intensity, so I'm taking your example now, but the phase of the electromagnetic field is a gauge for the intensity. But there's many more examples. I mean, the fact that Newtonian physics can be done in any inertial frame itself is a gauge, because it means you have the mathematical freedom to choose your inertial system without changing the physics. That's what we call a gauge. And it's quite ubiquitous. Let me give you one more, because people always like to see connections with quantum mechanics, but here's one. If you have solved the Schrödinger equation, you get your psi, right? And you know that if you take the psi squared, modulo squared, it will give you the probability distribution. It will tell you how big the probability is that the particle is in this location, right? This is your basic quantum mechanics, okay? But you know what? If I would have multiplied this with e to the power I times any function, the e to the power minus I, the e to the power I lambda, would have given you this. I would have stuck an extra complex exponential in there, regardless of what lambda is, the modulo square would cancel these out, and you would have gotten the exact same probability distribution as you would have had without the extra thing. Actually, Giovanni, this is a phase. This is the phase of your Schrödinger wave function. So that again is what we call a gauge. You can do something to the mathematics, in this case, add a complex exponential, but the physical measurement, in this case modulo square, does not change at all. So that general statement is what we call a gauge. And they come in all kinds of shapes and forms in physics. And in our case, that's our gauge. You can choose it mathematically in any way that you want, but your physics will stay exactly the same.
I have a question.
Yes.
Are gauge symmetries like this one always linked to a constant quantity?
Yes, it's notice theorem.
And is there a constant quantity in this case?
Yes, actually. That's a very good question. Yes, it's charge.
Okay. That's
What
cool.
is concept quantity?
Care to elaborate?
Constant quantity is a quantity which value needs to be preserved.
Doesn't change in time. And there's this notice theorem that tells you that if you have a freedom in your, well, officially in your Lagrangian, but let's not use that word here, but if you have a freedom in your mathematics without changing the physics, then that means there must be some conserved quantity. And we have this freedom here. Giovanni's question was, okay, there must be some conserved quantity. What is that number that is not allowed to change? It's charge. So all of a sudden, this thing doesn't just show you that you can make equations simpler, it also tells you that charge is conserved.
Because charge is invariant as well, right?
It's also invariant, but that's not his statement. His
Yeah,
statement
okay,
is that
but
it's constant.
okay.
So gauges are ridiculously important in physics. I mean, we use it here as a mathematical tool to make our equations simpler, but they have physical meaning too due to notice theorem. In this case, the conservation of charge.
But this is so crazy. Like
Crazy beautiful is what you mean.
Like I really would like to see like the more mathematical connection between, because like if I see that, it kind of looks abstract. And then we have this result which is super concrete.
Yes.
Which is that the charge is conserved.
Yeah, but let me actually connect it to Joyce's question when she was asking before, if I recall correctly, can I give a physical interpretation to it? Yes. So those two questions are related. So this is very abstract, I agree. I mean, mathematically we can show that this is the case, right? Now, let me answer her question first, and let's see if I can connect it to yours. Her question was, is there any physical meaning to this lambda? This, by the way, we call a gauge field. Okay, a scalar gauge field in this case. Is there a physical interpretation to it? And the answer is yes. And I think the easiest way that I can explain it is by analogy, namely using energies. In fact, in relativity, a similar discussion at some point came up, if I recall. Namely, do you remember that energy, the number for energy by itself doesn't give you any physical information? It's a change in energy that is related to something you can measure. Okay? So that means you can add to energy any number that you want, as long as the change has stayed the same. So if you will, you can change the 0 point of energy. If you took all energies in your system and to all energies you add plus 200, the changes between energy levels would still be the same, because the 200 would drop out if you subtract everything again, right? So that means the 0 point of energy is what you call, nobody does it in that way, but you could call it a gauge. Now, that is a general statement of physics, that usually you are able to write your physics in terms of new numbers that we call potentials. Energy is is in that sense a potential, that themselves do not have any meaning, but their derivatives have meaning. From Newtonian mechanics, the most easy example would be this. The gradient of the potential energy gives you the force, right? So the potential energy itself is what we call potential. Now, potential by definition means a thing of which you take derivative and then you get something you can measure. But here you see what I mean, because you can add 100 to it, it will just drop out of the derivative. We have done the same thing here. We've taken something you can measure, a B field, and turned it into some other guy's derivative. And because you turn it into some other guy's derivative, you all of a sudden have gained the freedom to add numbers to it or subtract numbers without changing the outcome. Just like here, we could have added 100 to 200 because it's the physics itself is defined as its derivative. The 100 will drop out. Here the same. We've defined our physics in terms of a derivative, a complicated derivative, but it's a derivative. So that means you have gained the freedom to add constants to it. Now this guy is not necessarily a constant, but that's because of the vector properties of this equation. But it's the same idea. The fact that you've replaced physics by a derivative means you have introduced a new freedom, and that's your gauge freedom. That's the best I can do to give you a physical explanation.
You mentioned this in special relativity for some. It's like the origin point, right?
Yes, exactly.
Yeah.
Yes. We were talking about this because of the MC squared part. It has nothing to do with this, but it's the same argumentation.
Yeah.
Okay, now, to me that fixes all of this. Yeah. So yes, one more time, this guy, these two equations. The first one tells you that there must exist an A. So if you want, this is just the second Maxwell's equation is just another way of saying you must be able to write things as a vector potential. That gives you this. I'm going to add Joyce's question in here now too, because you can now define it as a derivative. That means you have gained a certain amount of freedom. That's the gauge freedom here. And if you then want to know how A behaves, you have to take the fourth Maxwell equation, and then you end up all the way here. So that gives you hopefully a new interpretation of the Maxwell's equations. The second Maxwell's equation tells you vector potential must exist. And the fourth Maxwell's equation says, oh, and it behaves like this. So there's that. Upshot, we have solved all of magnetostatics right now. Everything is in there. Let's do the same for electrostatics. So I'm going to remove this, because we've taken care of these two now. Let's take care of the other two, and then end up with our four equations that we were promised to end up with today. Now, so these two are completely accounted for. So we have two Maxwell's equations to go. Let's do it right here, right now. We're going to look, if you recall, to the situation where there's no changing electromagnetic fields, right? It's a static situation that we're now looking at. That means that the third Maxwell equation will now be 0. Okay? Here's another mathematical factoid. This is mathematics. It's nothing to do with physics whatsoever. The curl of any gradient is always 0. Huh. Look at this. It's the curl of something. And it should be 0. Then maybe this can be written as that. So from this mathematical factoid, the fact that this is always true, we get that the electric field can be written as the gradient of yet another new function. Now the book calls this capital V. I don't, if you want to look this up. The reason is that capital V's in other contexts usually means either potential energy or part of Lagrangian, and I don't want you to be confused. And if you look in any other literature, phi, the one that I write down, is the standard notation. So if that confuses you, just replace this phi by a capital V and you're okay with the book again. But it's the same reasoning. So again, the fact that in statics the curl of the electric field should be 0, and that mathematics says, well, the curl of a gradient is 0, tells you that you are able to write the electric field as the gradient of a new function. Convention-wise, it's no physics there, but convention-wise, they defined it with a minus sign. I hope you see that doesn't matter, right? Plus or minus, it will still be 0. That takes care of this equation. Using Maxwell's third equation, we have proven that the electric field can be written as the gradient of a scalar function. Now, isn't that good news? Because look, this was 3 equations originally, right? This is only 1. Well, it's still 3 equations, but you only need 1 number now to get all 3 of them. Good, more reduction, getting closer to the number 4 equations that we want to end up with. Closer and closer. Now, this point just says you can write the electric field as a gradient of a new thing. This is what we call the scalar potential. But we haven't said what the scalar potential, how it's given. I guess we just know that the electric field is related to it in this way, but we haven't said if I give you a charge, what does the scalar potential look like? So any suggestions how to get that one?
Maxwell 1.
Yeah, we've used all the other 3. So let's go with this one. Right? So let's do that. So we now know from Maxwell 3 that E is minus gradient of 5. Then Maxwell 1 allows us to rewrite this E into this 5. So let's do it. So you get the divergence of E, which has now become the divergence of the gradient of this new thing, equals, I'm going to take the minus sign to the other side, minus rho over epsilon 0. So now we're there. And in fact, this guy together this is exactly that. Now, again, that's good news because we've now collapsed 1, 2, 3, 4 Maxwell's equations into one scalar equation. We've lost 3 equations now. So it means that this guy plus the 3 equations for A, those are the 4 numbers that I promised we would end up with. Now, no issues here with gauges, right? We use the gauge in the magnetic case to make equations look simpler. Well, this is as simple as we can make it. Wouldn't it be nice if we had the general solution to this equation?
Isn't that the same?
It's the exact equation. It's the exact same equation as before. So this again is what we call the Poisson equation. Its solution has been well known for a couple of centuries. There we go again. If you want to know the scalar potential at a particular position, and I've given you the charge density as a function of space, then you get 4 pi epsilon 0 1 rho. In fact, maybe you can help me put in the details, given that I've already shown you how the vector potential works.
So rho according to sweeping line?
Sorry?
Rho according to sweeping line?
Yes. So we sweep over volume and to look where all the charges are. That's our R prime. Divide by something.
Big R.
Big R. Do we need a direction? R hat? No, because we're looking for a scalar. We put in a scalar, so we don't need any vectors. And then we integrate over all volume. And this equation solves all of electrostatics. We don't even need the whole gauges part anymore. So let's summarize. Let's summarize. All these 4 equations are collapsed into 1, 2, 3, 4. By the way, I say 4, this is 8, yes? 1, 2, 3, 4, 5, 6, 7, 8. Completely collapsed into 1, 2, 3, 4 equations. And not only that, this is already the solution. You don't have to do anything anymore. If I give you a charge density, this guy, or I give you a current, or both, you just put them in the appropriate integral. You still have to do the integral. You get your A field, vector potential, you get your scalar potential. Once you have gotten the scalar and the vector potential, and you want to then turn it into E fields and B fields, fine. Once you have this number, take minus its gradient, you have the electric field. Once you have found this one, take its curl, and you have the magnetic field. 4 numbers.
Why did you, I'm sorry, why did you say that the first one was 3 equations?
Which one?
It's a vector. Oh.
Yeah, it's a vector, yes.
So 3 numbers, okay.
Now, not only is this practical, because you don't have to solve 8 equations at once now, given a rho and a j. You only have to solve 2. Well, 4, but they all work exactly the same. And you just have to remember one integral. Just do the integral. And that's it.
Question?
Yes.
What is the advantage of using the fields instead of the potentials?
Well, there's more multiple ones. One I've already mentioned a couple of times is that you have less equations to worry about.
No.
Oh, sorry.
The other way around.
Like what is why would you use this?
Yeah.
Nobody does.
Why do we use that?
Because it probably has to do with the abstractness. An electric field you sort of have an idea about, right? There's this stuff hanging here that's trying to pull you in one direction, and that's harder to say with rhos and with A's and with phi's. Yeah, I think it's mostly historical. No, actually there is a point. Because ultimately at the end here you get your E and your B. But if you then want to calculate in which direction particles are actually being pulled, right, then you have to, if you want to know the total amount of actual force on a particle, you have to put it into the Lorentz force equation. Here's the electric force, here's the magnetic force, the Lorentz force. And in order to use this equation, you need your E and B fields. So I think it's part historical. This is the way that they were found originally, and this was only found later.
Maybe also for just understanding more deeply these potentials.
I think it's easier if you're new to electrodynamics to first learn these and then move on to the potentials than the other way around. In that way, it's very similar, I think, to Newtonian physics. I think it's easier to learn about forces and only later learn about Lagrangians. Yes, because the latter is more abstract. But there it is. Now, nobody, theoretical physics and particle physics, nobody uses these really. Everybody uses these instead. Okay, how are we on time? Because famously no clocks here.
15 minutes.
To go?
Yeah, to go.
Good. Because there's one glaring point that we haven't addressed.
Non-constant magnetic.
Yes, we're looking at statics. And we would like to know, yes, but the original Maxwell's equations did not say that this is 0, and also did not say that this one was 0. So that means what we found here only works at the moment that things that there's no changing electric fields and changing magnetic fields. Or, which is the same statement, that the charge density does not change in time and that the currents are exclusively steady. And generally, of course, that's not the case. So we're going to keep this. So you can still remember this. In fact, let's call this all of electromagnetic statics. And I do mean all of it, because all of it is in there. We really built in all the 4 Maxwell's equations. But it is statics. Now, let's redo the exercise. We can actually be quite quick about it because we've done most of the work already. Let's redo the exercise. But now let's put back the derivatives. So, keep this aside. It's fine. We're going to rederive everything, but now in a slightly different way. So I'm reinstating the time differences. Now let's be very quick. Claim. Let's see if you can fill in the details yourself. Claim. This guy is still exactly the same, even in case of electrostatics. Actually, no. I'm pointing at the wrong equation. This guy. This is what I meant. This has not changed. You can still write the magnetic field as the curl of the of some new thing, the vector potential. Is that true? We know it's true in magnetostatics, but is it true in magnetodynamics? The answer is yes, but can you see why?
Which one did you point to? I'm so sorry.
This one. My claim is that has not changed. You can still write the magnetic field as the curl of the vector potential.
When we established it, we didn't start saying that the changes were zero. We only did that when we looked at the fourth equation, right?
Yes, we used the fourth equation to say what rule A itself obeyed.
But before that, we didn't say that it was electrostatic.
Exactly. We got the existence of the A field, the fact that you can write the B field as the curl of A, from the second Maxwell's equation. Well, that guy has not changed. So that means you can still write the B field as this thing. So that is still okay. Good. Unfortunately, the equation that it has to obey, that one has changed though. So this is why I pointed at this alternate equation, which is not true anymore. So one more time, we used divergence of B to prove that B can be written as the curl of some new thing, vector potential. But if we want to know how the vector potential moves in time and space, we have to do something else. So let's redo that exercise. How do we do this?
Let's plug it in again. And
Just plug it back in, yes. So let's do that. Curl B. And curl B is now still that thing. That has not changed. Equals 0j plus this, that. And now this extra part that we did not have before. That's this. And this combination we already used before, that you can rewrite this itself in a nice way. This one becomes, I'm going to get a minus to the other side.
Is it just a dot? Yeah, okay.
The gradient of divergence, that was this, that's a mathematical statement. This is a plus now. You get this now. If you leave out this, you get the same equation that we had before, and you could have used the gauge again to make this guy disappear. Now it looks like this. There's nothing we can do about this. That's the Maxwell equation with this extra part. So yeah, you can still, in dynamics, not statics, but in dynamics, you can still write B as the curl of A. It's just that the A has to obey a more difficult expression. It now also becomes dependent on the E field. All right. There is a gauge issue again, because we saw before that you can rewrite A into a new A. That's what we call the gauge freedom, without changing the resulting B. So that means you have a whole plethora of different A's to give you the same B, and maybe you can use your A again, your freedom in A, your gauge freedom again, to make this one look simpler. For instance, you could again choose your gauge freedom such that this guy is gone, and you would already have a simpler equation. Yes. We're going to choose a different gauge, a different choice. But it's possible in principle. It's just not the best choice. Now let's park this for a moment. Let's now go to the E field, the electric field. So, claim. This does not work anymore. Do you see why that is?
Because the curl is not equal to 0. And this
Yes.
we got when we assume that it was equal.
Exactly. we got this equation, the fact that you can write the E field as the gradient of a scalar function from the fact that the curl of the E field had to be 0, but it's not 0 anymore. So this one we can still use, this one we cannot, we have to alter it. I will tell you what the alteration is. And then you can prove for yourself quite easily that it is true. What's this? Shall we prove it? Because I just make the claim. My claim is that yes, this doesn't work anymore because the curl of E is not 0 anymore, but it's something else. But my claim is, oh, but wait a minute, if you now choose E to be the gradient of the scalar function, scalar potential, and you subtract the time derivative of the vector function, then this one is obeyed. And if we can prove that that is the case, then this rewriting is allowed. Shall we check if this new version...
Hold on, I'm sorry.
Okay. Parsing.
Okay, so the first part is saying that it only held if it was 0.
If this
Yes,
one was 0.
if the curl of E was 0.
Yes.
And then we're saying that if we add that in, which is how Maxwell has it, then it will give us the answer.
Yes.
And A is...
It's the same A as before.
Right, okay,
Now,
okay.
Maybe there's a way to show
Here.
this to just show you. So if this choice is allowed, if this is a correct choice, that means if we were to substitute this E back into here, you should get back dB dt, right?
Mm.
Let's see if that works. So let's see if we can make this question mark into an exclamation point. See if this works. Well, the curl of E should equal minus dB dt, but according to our choice, E is this guy here. Put the minus in front, then I get the curl, that one, minus dA. I get this, right? I just substituted this E for my ansatz, my guess here. I once again forget what the name is.
Distributed?
Thank you.
Yeah.
The difficult version of say you can just do the curl on each and then add them together. Okay. Yeah, my English is lacking. That's the problem here. As long as my physics is okay, I think I'm good. This part is still 0 for any phi. That's our original argument when we didn't have this part. That the curl of any gradient of any of the gradient of any scalar function should give you 0. So this guy is still 0. 0. Minus the curl of the ADT. That's operated on that one. And if I'm not mistaken, a space derivative and a time derivative can be swapped. So let's do some advanced swapping here. I get the ddt.
Wait, can you swap the cross product? Oh,
Yeah.
okay. That one.
So we can do this.
Wait, but doesn't the cross product like make it? Does the cross product matter in this case or not?
No, it matters, but the only thing that matters for the argument of swapping is with respect to what variable are you taking.
Oh,
And
okay,
it's a
okay.
space variable, and you can swap it with a time variable.
So it's like taking out the constant.
Yes. Now look at this. We now have the time derivative of the curl of something. And we just concluded that even in dynamics, the curl of A is what we call the B field. So this apparently is the ddt of the B field, and that's exactly that.
Oh, I feel. Sorry.
No, it's good. It means that we still know how to make an electric field in the dynamical case. It's just not anymore only the scalar potential that you need. You now also need the vector potential. But this combination will obey Maxwell's third equation. So this is what we're going with from now on. That means this one is now accounted for. Yes? So this is now exclamation point. Not to be confused with factorials. That's not what I mean. I just mean it's now proven. It's not a question anymore. yes, we can obey Maxwell's third equation as long as we write the electric field in this particular combination of the scalar and vector potential. But the only thing we've done now, we have proven that the electric fields can be written in terms of the potentials. We haven't shown yet what the potentials have to obey. So what do we do?
We plug this into the first Maxwell?
Yeah, we've used all the Maxwells, right? We've used these two to get the magnetics in order. This one we have now used to prove that you can write the electric field in this way. There's only one Maxwell equation to go, and that one will connect all of this to the charge, and therefore we should tell you something on how these things move. So let's see what happens. The divergence of electric field is now given by this guy. I'm very sorry, but this is going to look crappy. Okay? Divergence of this minus the divergence of dA dt. That's this. This is okay, yeah? Okay, yeah, I'm not skipping anything, good. This together, the divergence of the gradient, is what we call Laplacian. It's another way of writing the same thing. I'm going to bring a minus to the other side. This question for a moment.
Yes. Okay.
Yes. I feel like I'm missing a term, but I'm reciting from memory, so I could be wrong.
This time you're giving us time to digest
Yeah,
this.
it also gives you time to check whether what I'm doing is okay. It is. Okay, good. No, I was reciting from memory, but you know, at some point memory loss starts to kick in, so I could have been wrong, but this is okay. All right. Let's make some big blocks. I hope the red one works. Sure, otherwise somebody, maybe renames it, somebody will have a red marker. There we go, thank you. Okay, so. We're now in the electrodynamics case. And as you can see, the idea is still the same. You can write all of your electric fields, magnetic fields in only 4 equations, 1, 2, 3, 4. So that goal has still succeeded. It's just that these equations are much more difficult to solve than when we're in the static case, right? Unfortunately. So we're not too happy here. So yeah, yeah. Let me point out what the difficulties are. One of them is that these 2 equations are now coupled. If I want to know what the phi field is, the scalar potential, in the statics case, I just needed the rho, right? I just put the rho into here, do this integral, I get my scalar potential. But unfortunately, knowing rho is not enough. I now also need the A field. Okay, so where do we get the A fields from? Well, maybe you can get it from this one. Yeah, that's true, because then I also need the charge, or sorry, the current. And then if you give me the current, I can maybe solve for the A field. Oh, but the A field, well, it has an E in here. And the E itself depends back again on the phi. So it's become a coupled system now. You cannot solve this one and use its result to solve that one. Or to solve this one and use its result to solve this one. You have to fix them in one go. It's a coupled differential equation system that makes it very complicated, unfortunately, in practice.
So there's no magic to simplify those?
There is. Because there is one clever trick that we use in the statics case, not in the dynamics case.
Like choosing what your A is.
Yes, we had the gauge freedom. Remember, you could choose A in different ways without actually changing the B field. So we had this whole plethora of A's and A primes that we could use, and if you choose them in a nice enough way by a clever choice of your new A prime, then the mathematics cleans up and you have not changed the resulting E and B field. Right? That was his gauge freedom. Now, there is a choice for the gauge that is going to highly clean up these two equations. Actually, there's two choices in literature. I would tell you one of them, that's the one we're not going to use. But I want to show you that you can still do it. Before, in the statics case, we chose the gauge such that the divergence of A is 0. Right? But you can still make that choice. It was just based on this equation. This has not changed, so you can still make that choice. So if you want, you can choose the gauge, again, that this is 0. Well, it cleans up a little, but not a lot. But there's a different gauge. Time. Just
2 minutes past.
2 minutes past. Should we make it a cliffhanger?
It's up to you.
Yeah, we do it in the tutorial, that's okay. But let me tell you what the answer is, yes? There's going to be a gauge that not only is going to make both of these equations much more simple, so we're going to choose a new A field such that both of them become much more simple. Not only that, they become uncoupled. That means you can solve them separately from each other. Here's the better news still. Just like in the statics case, both of them will be the exact same differential equation. It will be different than in statics, but A and phi will have the same differential equation. So that means you only have to remember one solution, and I'm going to also tell you what the solution is. So yeah, let's do that in the tutorial. But once it's cliffhanger, yes? But by the end of the day you will get the answer. There is a gauge such that these two uncouple, become much easier, look exactly the same, and I will give you the general solution to it. So we'll get something like this, but now for the dynamics case, and then we have solved, and I'm not joking or being flippant, we have solved all of electrodynamics, because all of Maxwell's equations are in there, and I'm going to give you the general solution. But we still have a tutorial to do this in. Cliffhanger.
One question.
Yes.
It's about